Welcome to step 3. And now we're going to talk about radiation. And radiation is really cool, and it's a really important part of environmental science. Now, you know, I'm a cheerleader for the atmosphere by this point, and radiation interacts and is interconnected to our atmosphere in a really important way. And so in order to understand those interactions between radiation and the atmosphere, we're really going to sort of delve into radiation first. And what is a radiation? What is radiation? So before we begin, though, I'm just going to back up. I want to remind everybody about the composition of the atmosphere. That's nitrogen, 78%, oxygen, 21%, argon, about 0.9%, water vapor up to 3%, and carbon dioxide, about 400 ppmv. It used to be about 285, which was about 0.03%. Now, notice that those numbers don't add up to 100, and that's because as water vapor increases or decreases, it sort of shoves everybody out of the way. And if water vapor goes up to 3%, that means nitrogen, oxygen, and argon all decrease as well to make room for that water vapor. At the equator, where it's nice and hot and muggy and humid, you can have up to 3% water vapor in the atmosphere right above sea level. Oftentimes at the poles, where it's cold and very dry, any kind of water vapor generally tends to freeze out and get deposited as snow. So it's very dry up at the poles usually. The important thing also to remember is the structure of the atmosphere. And you'll notice in that first video, I'm sort of waffling around where is the boundary between the troposphere and the stratosphere, and talking about that 10 to 12 to 15 or 13 kilometers as an important part of our atmosphere, because it holds between 80 to 95% of our atmosphere by mass. And the reason I waffle around those numbers is because those numbers actually change. There's no hard boundary between the troposphere and the stratosphere. And that's because the troposphere actually increases in height and decreases in height with temperature, and also changes in height as you go from the poles to the equator. But do notice over here where it says 100 millibars, that is 90% by mass of our atmosphere is below that, because at sea level, we're at 1,000 millibars or 1 bar of pressure. So somewhere between about 12 to 15 kilometers is where we've got about 90% of our atmosphere. And really, it is a very small part of the atmosphere with respect to altitude. There's actually other layers of the atmosphere above the thermosphere as well. But just remember, we're really talking about this important layer down here, the troposphere. And when we're talking about ozone, we're talking about stratosphere. And in fact, this increase in temperature is because of the interaction of ultraviolet radiation with ozone. Look, this stuff is not top secret. It's not inaccessible to most people. You can understand radiation. It's really important to understand. And I tell you what, it's super useful. And we use it every day in our lives. And not only in, well, hopefully we don't use infrared missiles every day, but every day we do use infrared cameras or infrared sensors. And so knowing about electromagnetic radiation and how it interacts is important. This is just a cool little example from, I think, the Boston bomber. He was a terrorist in the United States who tried to hide from the police. And the police eventually found him hiding under a boat cover in a boat in a backyard by using an infrared camera. And because infrared wavelengths of light penetrate the canvas cover, the camera was able to detect that there was a person who had a temperature about 310 Kelvin, which is minus 275, about 40 degrees Celsius, 36 degrees Celsius, above the background. That's a person in there. So they found this guy and were able to arrest him. So it's electromagnetic radiation. It works, and it's useful, and it's really interesting. What is electromagnetic radiation? Look, we're all familiar with light, which is the visible portion of electromagnetic radiation. And we use the word spectrum because electromagnetic radiation comes in different kinds, for lack of a better word, different types, but it's all on a spectrum. It's not specific sets. It's all on a continuous spectrum. That's what I'm looking for. And from very short wavelength, high energy gamma rays to X-rays, which we're familiar with if we ever break a bone or go to the dentist, ultraviolet rays, which cause damage to our skin and we wear sunblock for, visible light rays, which we're all very familiar with, infrared, which are warmth. We can often feel those and sense infrared wavelengths. Microwave we use to heat up our dinner, and radio waves we use to listen to music in our car. Now, each of these waves has a different range of wavelengths, which is simply the distance from the tip of one crest to the tip of the next crest. And notice that the wavelength can be anywhere from the distance of some tall radio buildings, so in the hundreds of thousands of meters long, whereas when we get to visible light rays, we're dealing with, I believe it's, is it micrometers, I believe, micrometers. And infrared wavelengths, you're looking at something that would sort of be the same size as a needle point. So give you some idea here. And the wavelength is inverse to the frequency. So the shorter the wavelength, the higher the frequency, because all of these electromagnetic radiation travels at about 300 million meters per second, which is the speed of light. Okay, so you can imagine that short wavelengths moving past an observer would have a very high frequency, whereas long wavelengths moving past an observer at the same speed would have a much lower frequency of seeing that crest. And that's sort of how that works. It's also a fact that different objects at different temperatures will emit radiation at different wavelengths, and it tends to be that the hotter the object, the higher the frequency of radiation will be. Okay, and remember, frequency is down here, which means the shorter the wavelength. So just kind of wrap your head around that. Just let it all wash over you. The important thing to remember here is that electromagnetic radiation occurs in different frequencies. And as I'm teasing up here at the top, some of those frequencies penetrate the Earth's atmosphere and reach the Earth's surface, and some of them do not. Okay, we'll talk about that in the next step. But right now, let's just focus on radiation. Look, when we look at radiation, we use a sort of a thought object called a black body. Now, a black body is an object that absorbs and emits radiation at the maximum rate for any given temperature, which means if we've got a cold black body, okay, it'll emit radiation on sort of the left-hand side of the scale in radio, microwave, or infrared wavelengths. If we have a hot black body, like the sun, okay, at 6,000 degrees Kelvin, it'll emit high energy, short wavelength frequencies. So visible, ultraviolet, okay? And we'll get those kinds of wavelengths from a really hot body. So black bodies are an important way of thinking about radiation. Now, I will just tell you that Kelvin is essentially a degrees Celsius, but it's got a different sliding scale because it goes from absolute zero, which is at 0 Kelvin, to 275 Kelvin is 0 degrees Celsius. So there's just a 275 degree difference between the Celsius scale and the Kelvin scale. And when we're dealing with temperatures like 6,000 degrees Kelvin, you know, you're not going to notice the difference between 6,275 degrees Kelvin and 6,000 degrees Kelvin. So you can just think of Kelvin as a sort of like Celsius, but we'll this is what it looks like in sort of practical terms. Look, a black body absorbs, we just talked about this, a black body absorbs and emits radiation at the maximum rate for any given temperature. Now, that means Earth, if we think of Earth as a black body, it will absorb the radiation from the sun and re-emit that for whatever temperature it's at. And it just so happens that on average, the Earth is about 290 degrees Kelvin or 15 degrees Celsius. That's the average temperature of the surface of the Earth, right? And because that's what's emitting the radiation, is the surface of the Earth. Relatively low energy, relatively long wavelength. So we're talking about the infrared spectrum right now, okay? The sun, 6,000 degrees Kelvin, really high energy, really short wavelength. I'm going to tease the next, we're going to see this in the next step again, but I want to just tease right now that the energy from the sun that impacts on the Earth is the same amount of energy that the Earth re-emits as a black body object, okay? Whatever energy comes into the Earth isn't stored in the Earth's core or anything like that, okay? Whatever energy arrives at the Earth's surface from the sun is re-emitted out into space by the Earth's surface, okay? Now, there's a bit of a piggy bank in the atmosphere. And this is where we start to talk about global warming and greenhouse gases, okay? So there's a bit of a delay between that radiation coming in from the sun and that radiation being re-emitted back out into space. And what I'll notice here is that we've got sort of equal energy in, equal energy out. And on the x-axis down here, this is an exponential axis down here, a logarithmic axis. And this over here is just a linear axis. But notice that the energy coming in from the sun is the same area under this curve of the energy coming in from the sun is the same area as of energy under this curve here of the outgoing terrestrial. They're equal areas, meaning an equal amount of energy coming in is an equal amount of energy going out. Now that outgoing terrestrial radiation, look, is it spread across these longer wavelengths, whereas the micrometers, sorry, microns. And whereas the incoming solar radiation is these very short, high energy wavelengths. And you know this intuitively, because if you go outside during the daytime, you'll feel that warm, hot sun on your skin. And then if you go out at night, just after sunset, go out and feel a rock or a sidewalk, and you'll still feel that radiation coming off the rock. It'll be infrared radiation instead of that bright ultraviolet and visible light radiation. There's infrared radiation from the sun as well, okay? It's not just this the visible and the ultraviolet, but a lot of that incoming radiation is in that spectrum. And so what's happening is essentially that energy that's, and remember our first law of conservation of energy, energy is not created or destroyed. We're simply converting the energy that we intercept from the sun. We're converting it from short wavelength, high frequency radiation. The Earth absorbs that. And then because it's a black body, or it behaves roughly equivalent to a black body, it emits that radiation in a longer wavelengths, because the temperature of the Earth is far lower than the temperature of the sun. Now, we're just going to remember this difference in incoming solar radiation wavelength versus outgoing terrestrial radiation wavelength for our next step.